Welcome back to ECE 441A 541A. Homework number 5 is due Wednesday. Exam 2 is Friday with a fair number of topics. They're listed there, but essentially we have 5 general areas, and so you'll have 5 problems is the idea. Lab number 2 is due a week after exam number 2, but lab number 2 is dealing with material that it will be on exam number 2 in terms of design specifications, or where are your S-plane poles located to achieve certain performance specifications like settling time, percent overshoot, and peak time or rise time. You need to know that, obviously, for exam number 2. Today we will look at the sort of final topic for exam number 2, which is the Routh array, or the Routh-Hurwitz criteria. This is now the array constructed as the second part of this Routh array criteria. I've listed really sort of the 3 cases that the Routh array may fall into as you're building it. We'll try to go through those, and we will try to examine a Routh array with an adjustable parameter. You can also look at some of the material on D2L concerning, well, previous exams. There you will see some problems that deal with this Routh array with an adjustable parameter. To get us started, and I tried to color code this, I don't know that that's clear, but the Routh array examples that we will go through, let's just remind ourselves of what we were doing when we were building the Routh array. We have this nth order polynomial. N could be even or odd, it doesn't matter. We just need to know what's the highest power of our S in that polynomial, and that then produces the top 2 rows in our Routh array. Meaning the green coefficients, the first one, a sub n, then we skip over a power of s, and we go to the next power, a sub n minus 2. Then we skip over a power, and we go a sub n minus 4. Those are the coefficients that we use to build the first row of our Routh array. The second row in our Routh array is we start with the coefficient associated with the power of s 1 less than the highest, and then we simply go down from there. We go a sub n minus 1 to a sub n minus 3 to a sub n minus 5 until we run out of coefficients. Then we can build the rest of the Routh array, and I'm just labeling those B1, B2, C1. Then we get all the way down. We keep going. The bookkeeping is on the left. That just sort of tells you how many rows I should be generating in this Routh array. And you will get down to the s to the 0, or the constant row, in your construction of the Routh array, and then you can start to make some decisions. Let's review your homework assignment that was given to you last time. You had the entire weekend to do it. Did you perform the Routh array or build the Routh array for this monic second order polynomial? And if you didn't, can you do it now? Can you create the Routh array for this second order polynomial? And if you've already done your homework, this should just be writing down some numbers. Actually, it's writing down coefficients. There are no numbers. We're trying to do this for a generic second order polynomial. And this will now give you insight. Anytime you see a second order factor, you'll be able to tell, are the roots of that second order factor, are they in the left half plane or not? In building up your Routh array, what did you do first? Did you decide to do the bookkeeping? The bookkeeping is nice, I think, meaning if you now just have that on the side. So if you're ordering your meal, you can just say put those powers of s on the side. Those are now this column of s's, s squared in this case, s to the 1 and s to the 0, that will allow us to keep track of what we have and where they need to be located. In the first row, what did you put? 1, then you skip over and you go a sub 0, right? That's the first row. It's just 1 and a sub 0. Again, the top 2 rows of your Routh array come directly from the coefficients in your given polynomial. Did you have anything in your second row, the s to the 1 row? Now you just look down, you say, okay, I have an s squared, that's my highest. I go 1 less than that and start the process. I look at the coefficient of the s term, which is a sub 1, and I then run out of coefficients. I don't have a coefficient underneath a sub 0. That's okay. Now I want to build the last row in my Routh array, and how do I do that? It's sort of this backward determinant thing, isn't it? It's a1 times a sub 0 minus the product of 1 times nothing, so you just put a 0 there, divided by a sub 1. What did we just do? We were trying to build up this b1, and b1 is a1 a sub 0 minus 1 times 0 over a1. Now something magic sort of happens. The a1s cancel, and really because of this non-entry there, or this 0 piece there, this a sub 0 actually just drops down, and you didn't have to even calculate that b1 directly. You could just say that's a sub 0. Is that clear? It falls out if you do the math. Yes? Why do we put a 0? Why do we not have anything there? We don't have anything in that red, that looks like an egg to me, a fried egg. In the fried egg location, we now have the yolk as our 0. Is that okay? Yeah, it's just why don't we implicitly write it there? So we could have explicitly put a 0 there, and then that would help you if you want. That's fine. You can either put it there or not, but I'm basically saying you've run out of coefficients, so you wouldn't have something there necessarily. But if you say, well, I run out and I kind of want to fill up my array to make it look nice and square, I'll put a 0 there. Anything that's missing, you can fill in with zeros. You could just keep going with zeros if you wanted to, but that's just more work as far as beyond a sub 0. Now what do? We want to know, for this polynomial, s squared plus a1s plus a sub 0, when will that be a stable polynomial? When will all of the roots of that be in the left half s-plane, or when will all the roots have negative real parts? All the roots will be in the left half plane if we do not have any sign changes in that leftmost column. We do not want sign changes. We had a 1, that was a positive. So that's saying we want a1 to be positive. a1 positive, we don't want a sign change between a1 and a sub 0. That says a sub 0 needs to be positive. This now says, for this second order polynomial, for stability, we now need a1 non-negative and a sub 0 non-negative, which now allows us, for any generic second order polynomial or factor, if you factored a 10th order polynomial into second order pieces, or first order and second order. The first order is pretty clear where those are as far as roots. The second order, you don't need to plug them into the quadratic formula. You just need to know, are both coefficients there and non-negative or positive? Yeah, I shouldn't have said non-negative. They need to be positive. This is a strict inequality. Then you have all of the roots of that second order polynomial in the left half plane. So the Hurwitz test, really, since that says, are the coefficients all there, are they present, and are they positive, the Hurwitz test is actually a sufficient and necessary for a second order polynomial. And you wouldn't have to build this Routh array for another second order your entire life. You should be able to plug this idea into your head and remember it forever. If not, you can build the Routh array and convince yourself that it's true. The Hurwitz test is sufficient for second order polynomials. That's our first example with the Routh array. Let's now look at another polynomial. Suppose now we have s to the fourth plus 5s cubed plus 40s squared plus 180s plus 144. If somebody wanted to know, is that polynomial, does it have anything maybe in the right half plane, or is it unstable, you might perform the Hurwitz test. The Hurwitz test, how does it do on the Hurwitz test? Are all of our coefficients present? Check. Yes. Are they positive? Yes. Check. So what can we conclude? We can't say stable yet. We can say that it's not from the Hurwitz test. We can't conclude that it's unstable. We really can't conclude anything right now. We just need it to pass this test. If we wanted to, if we had a negative coefficient, then we could say, oh, we are not going to be all in the left half plane, all of our roots. But we don't have that now, and now we need more information. Let's now build the Routh array. If we build the Routh array, and if we do our bookkeeping, we now have an s to the fourth, s cubed, s squared, s1, and an s to the 0. We can populate the first two rows directly from those coefficients in our polynomial. Can you do that? And if you do, what's in the top row? $140 and $144. What's in the second row? $5 and $180. Everybody comfortable with that? So now you have 2 points out of 25 on your exam. It's better than 0. Okay? 1 point for each row. How's that? You don't even have 25 rows. Come on, Tharp, give me more than that. But you do have 5 rows, don't you? Now, how do you build the second row's first entry? What's it going to be? Fourscore and 7 years. How do we create, or how did you find 4? Where did 4 come out? Well, there's 4s all over the place, but there's no 4 by itself. We take 5 times 40, 200, minus 1 times 180, 200 minus 180, 20, divided by 5, 20 divided by 5 is 4. This guy here is 4. That 4 was the 5 times 40 minus 1 times 180 all over 5. What about this entry here? How do we build that one? We always use the leftmost column, and we always build from the row, 2 rows above us. So now we have 5 times 144 minus 1 times nothing, all divided by 5. 5 times 144 divided by 5. The 5's cancel, and that 144 just nicely falls into that puddle, or whatever that is, a cloud. Everything's the cloud these days, so I had to go to the cloud to get that number. Is that right? So now what's the S1 row going to be? The first entry. Actually, the only entry. We build from the 2 rows immediately above us, and we always work with the leftmost column. We have 4 times 180. Wow. So 400 plus 320, 720. 720 minus 5 times 144. 720. Uh-oh. Divided by 4. We're okay with the division, but our numerator was 0. So we actually created here, let me write that down. We had 4 times 180 minus 5 times 144 all over 4. That ends up being 0. Ouch. We can't go on, can we? Because we need to divide by that, and we can't divide by 0 if we wanted to build the next row. That's why we have to apply a different strategy. Now, the S1 row only has that one entry, and it's 0. So that's an all 0 row. Good. Now we can find this auxiliary equation and use it. Is everybody okay with S1's row being all 0? It's only one piece, but it's all 0. It's only one term. That's an all 0 row. With that all 0 row, now we need to create or find or use the auxiliary equation. And the auxiliary equation actually comes from the row one above the all 0 row. In this case, that is coming from the S2 row. The auxiliary equation, let me just call it A of S, A for auxiliary, and it's a function of S. We now have 4 and 144. What's the polynomial associated with 4, 144? And now utilize the bookkeeping. You know you're in the S squared row. That means the leading coefficient, the coefficient or the element in the leftmost column, is going to be scaling S squared. And then how did we build our Routh array? I apologize for those of you at home. You didn't see me jumping over a power of S. So we start with 4S squared. We jump over the S1 coefficient, and we end up with the 144 times S to the 0. Is it clear where that's coming from? Our auxiliary equation is from the row immediately above the all 0 row. That's the S squared row. This is now 4S squared plus 144. And now what we want to do is we want to populate the S1 row. We said we use the auxiliary equation to somehow inform what we do in the all 0 row. Now what we can do to make that polynomial one less in degree, differentiate it. So we differentiate the auxiliary equation and use that result, those coefficients, to populate the all-zero row. In this case, then, from this auxiliary equation, we have dA ds, and this is why we spent a whole semester in calculus to learn how to differentiate. We now have 8s. That's now going to be used to populate our all-zero row. What's the S1 row become now? We take that 8, and that now replaces the only entry in that all-zero row. If there was another entry, if this was a higher power auxiliary equation, we could have additional coefficients, and we would use each of those to populate the entries in that row that was all zero. Now, can we continue with the construction of the Routh array? Now we're not going to be dividing by 0. Now we can divide by 8. So I apologize, that 8 is underneath the 4. Is that clear? That 8 is now in the leftmost column of the Routh array. So you can erase or copy down in another location on your paper, but that red 8 is supposed to be right underneath the 4 in the s squared row. We use that 8. 8 times 144, don't multiply it out, minus 4 times 0, divided by 4, and we end up, or no, I'm sorry, divided by 8, and we get 144. That 144, again, just floats down there. Got a lot of things going on. Now what do? We count the sign changes in that leftmost column. How many sign changes do we have in that column? No sign changes. And what can we say about sign changes? That number, the number of sign changes, corresponds to what? The number of roots of that polynomial in the right half plane. We have 0 roots in the right half plane from the no sign changes observation. We have no sign changes. That's in the leftmost column. That implies in that polynomial that we started with, we have no roots. With positive real parts. But you want to be on all alert when you have an all-zero row or an epsilon that you have to introduce. Something happened. Something was going on. You should start to get a little bit nervous. So you say, but there was an all-zero row. Does that look like a flag? So that should alert you. That's a flag. If you have an all-zero row or an epsilon that you have to use to produce or continue constructing your Routh array. What that actually tells you, an all-zero row allows you to say the following. Therefore, the system, or really the polynomial that we started with, has roots that are symmetric with respect to the origin. The system or the polynomial has roots that are symmetric with respect to the origin. So what? Well, do we know anything more than that? Symmetry with respect to the origin. So if you were looking at the S-plane and you looked at the origin, you would say some of the roots are symmetric with respect to the origin. So if I had a root at +1, I must have one at -1. That's symmetry. But can we know any more? Well, we do know where that all zero row was. The S1 row was 0. That means the symmetry was a result of the row immediately above that. Immediately above the S1 row is the S2 row. So we have symmetry of 2 roots. That's because the row immediately above us was the S2 row, and that's the row that had the symmetry. That's why we had a 0 all row in S1, because of that symmetry in the row above us. That produced the symmetry. In general, how could we have symmetry in the S-plane with 2 roots? We could have that, or we could have that. Those are symmetric with 2 roots. If we had 4 roots, we have all sorts of pretty pictures for symmetry, right? We could have a plus sign. We could have a multiplication sign with 4 roots. But for 2 roots, this is how we have symmetry. This is in general. This isn't this specific problem. This is the general scenario for 2 roots that are symmetric. For our particular example, our S2 row produced what formula, or what polynomial? That was 4s squared plus 144 is equal to 0. Actually, the S2 row was 4s squared plus 144. If we set that equal to 0 to find the roots associated with those coefficients, we can divide both coefficients by 4. We now have s squared plus 36 is equal to 0. We now have s squared is minus 36, or s is now plus or minus j6. Our symmetry then was along the imaginary axis, and that's what we said. We said we don't have any roots in the right half plane from our no sign change result. So we combine that information, no sign changes, with symmetry. We say, oh, how do we have no roots in the right half plane and symmetry with respect to the origin? We can't have the picture on the left, can we? Because that has one pole or root in the right half plane. The rightmost picture agrees or is consistent with that conclusion that we reached with no sign changes. Is that clear? All right, let's look at another example of the Routh array. Is this example 3? Let's say delta of s is now s cubed minus 3s plus 2. If you were doing the Hurwitz test, yes. So plus or minus J6, are they actually poles of the system? Yes, we didn't even have a pole, did we? We were just looking at a polynomial. So wherever this polynomial came from, if it was a denominator of a system, then the roots of that would be the poles of our system. If you actually factor that, you better find that you have roots at plus and minus J6. So that now, in this fourth order polynomial, you do have a second order factor that's s squared plus 36. You could factor that out of this delta of s. So the question was, those symmetric roots that we found from our Routh array, all 0 row, and going one above to get this picture, do those actually belong to the original polynomial? And yes, they do. So here the question was, if those were poles, if this polynomial was in the denominator of our closed loop transfer function, is our system still stable? So we know all the other, we know we don't have any roots in the right half plane, right, from our Routh array. We do know that we have 2 on the imaginary axis. Some textbooks will say that system is marginally stable. I would say I wouldn't want to have that as a system, because if you go kick it, what happens? I don't think I'm moving at 6 radians per second, but it just keeps going and going. There's no damping. And if you were trying to be devil's advocate, you could excite that with a sine wave or a cosine at that same frequency, and it would start going unbounded. So now it's growing with t. So that's really, I wouldn't want to be there as far as a system, having poles on the imaginary axis, unless you're building an oscillator with that particular oscillation frequency that you want to have. Then that would be what you want. But no, I wouldn't consider this to be really a stable system. I want everything in the left half plane, and actually to be somewhat into the left half plane so that I have enough damping. Does that answer the questions? Are we clear on that? You've now learned a lot about a fourth order polynomial without even factoring it. All you really had to do was solve a second order polynomial. Luckily, because the s squared row was all 0. I'm sorry, the s1 row was all 0, and we had to use the s squared row as our auxiliary equation. Now this one. Here's a cubic. What can you tell me about this cubic and Hurwitz? It fails the Hurwitz test, doesn't it? And what does that tell us? System's not stable. So if that's the only thing, if that's the only decision you were asked, if I was kind enough on an exam to say, is this polynomial stable? You could say NO. And I couldn't take off any points. Could I? If that's all I ask, I would hopefully say why. I would put on my 2-year-old hat and say why. And then you would have to explain, why is that not stable? It fails the Hurwitz test. You could do that, and then I couldn't take off any points. Hurwitz, it fails. But on the exam, I'm probably going to ask something more like, tell me how many roots are in the left half plane, how many roots are in the right half plane, and how many roots are on the imaginary axis, by using the results from the Routh array. All right, let's build the Routh array. What's our bookkeeping tell us? S cubed, S squared, S1, and S0. We have 4 rows in our Routh array. Top row, no, that's not right, is it? That's not right. Still have my 2-year-old hat on. I'm just counting. 1, 2. You need to keep track of where your factors are, or your powers of S are. And really, you need to skip over the S squared coefficient, and that's not even present in that expression. We skip over that, and we end up with minus 3. That's the top row of our Routh array for this polynomial. Is that right? Now, what's the second row look like? It's not this, is it? No. We go 1 power less than 3, and we look and look and look for the coefficient of the s squared factor, and it's 0. And then we skip over the s1 and we write down the s to the 0 coefficient, and that's 2. This is now the completion of the top 2 rows of our Routh array. And now we fall into a different case. Now we have a 0 in the left column and non-zero terms in that row. So this is not an all-zero row. We can't use that. And if we wanted to go on, we would be dividing by 0, and we can't do that. What we do is we introduce an epsilon, a positive number, and replace that 0 with this epsilon. We put that epsilon right here, and then we keep building our Routh array. The S1 row is now minus 3 times epsilon. Ooh. Minus 1 times 2 all over epsilon. Did I do that correctly? And now I need to populate the S0 row. Oh, really? I have to mess with that ugly expression? Just be patient. What's sitting to that ugly expression's right? Nothing. So we have that ugly expression times 2 minus epsilon times 0, that goes away, divided by that ugly expression. What happens in the S0 row? That 2 drops in there nicely, doesn't it? So this comes down because of that open space. Are we clear on that? Now what we need to do is we need to count the sign changes in the leftmost column, and we do that as we let epsilon vanish. And epsilon is positive, so it's coming from 100 to 10 to 1 to a half. It's coming in from the right. Epsilon is approaching 0 from the right. We let epsilon get tiny, but it's positive. In the numerator, we have minus 3 times a tiny number. That's gone, isn't it? Compared to minus 2. The numerator becomes minus 2 as epsilon shrinks. What happens to the denominator? It's positive, and it's just making things bigger, isn't it? Dividing by a small number. But we remain, what's the sign of that third, or the S1 row? It's minus 2 divided by a small number, isn't it? That's not going to change the sign. That's why we pick epsilon to be positive, so that we can make these assumptions. What do we have in the left column? We now had a positive. Epsilon was positive, so that remains positive. S1, you just, I think, agreed with me that it was negative, and 2 is positive, which now allows us to say what about the sign changes? If we have 2 sign changes, what does that mean about the roots of that cubic? We have 2 roots in the right half plane. And you could find those with your calculator if you wanted to. Did you guys ever use synthetic division in 3rd grade or sometime? Teasing on the level where you might have had that. But our polynomial was s cubed plus 0s squared minus 3s plus 2. That 2 hanging out there in the constant sort of is begging us to guess that 2 or minus 2 might be a fact or a root of that. So let's just say that s is equal to minus 2 is a possible root of that. We have 1, then we have 1 times minus 2 or minus 2. We add those and we have minus 2. We have minus 2 times minus 2 or 4. We add those and we have 1. We have 1 times minus 2. So yes, it was a factor. S equal minus 2 is what this is telling us was actually a root of that original. And this tells us that what was, when we factor out that s plus 2 factor, we have s squared minus 2s plus 1. Or delta of s, we've now figured out, is this s plus 2 factor and an s squared minus 2s plus 1. And do you see how this quadratic factors? And now we have all 3 roots of that cubic. We now can see that we had a root of minus 2, a root of plus 1, and a root of plus 1. Is that consistent with our conclusion? Instead, we had 2 roots in the right half plane. We check it on our calculator and we get minus 2 plus 1 as roots. We go, yes. So you can work all sorts of problems because you have the way of checking your work. You can factor polynomials. Questions on that example? Yes. Can you use the Routh array? Not directly. We did it, so the question was, can you use the Routh array to find the zeros of your polynomial? And it's not really designed that way. You can use some of the information that you're gathering in the construction or the building of the Routh array to help you find those in certain cases. Let's look at a symmetry case. And it looks like I might not have time to get into the parameter, adjustable parameter case. Look at some of the old exams for that. I don't know if I'm going to do that Wednesday or not. But here, let's look at a symmetry example. Meaning, let's go ahead and build something, a polynomial. Let's build a polynomial so we know what we have and then apply the Routh array to it, and then we can figure out if we're doing the Routh array right. This is how you can test yourself on the Routh array. Suppose I want a polynomial that has a root at 0, a root at plus 1, and a root at minus 1. What does this look like as a factor in delta of s? That would be s minus 0, wouldn't it, or just an s. This one is s minus 1, and this one is s plus 1. Those are my factors from those desired roots. And I can simply multiply those together so that I now have s times s minus 1 times s plus 1, or I have s times s squared minus 1, or this is now s cubed minus s. So let's build the Routh array from that polynomial. It's a cubic. We had 3 roots, and we actually had symmetry with respect to the origin. We have a root at -1 and a root at +1. And we actually have a root at the origin, and that's kind of symmetric with respect to itself. So let's build up the Routh array. Where do we start? S cubed, S squared, S1, and S0. So we're going to have 4 rows in our Routh array. What's in the top row? What's in the second row? 0s squared, and there's no constant. There's an all 0 row in an even row. Here is an all 0 row. And what's our auxiliary equation then? We go to the row above, the all 0 row, and build up our auxiliary equation from that. And it's in the s cubed. That coefficient for s cubed is 1. Then we have no s squared, and we have -1 times s, which is really the original polynomial. But you don't need to know that necessarily in this process. We just go 1 row above the all 0 row, create our auxiliary equation, differentiate this with respect to s, and now we can use those to modify our all 0 row. What's the first 0 in the S2 row? Three. What's the second entry in the S2 row? -1. Now we can continue. We have 3 times -1 minus 1 times -1 all over 3. Or we have -3 plus 1, or -2/3. And what's in the S0 row? You have -2/3 times -1 minus 3 times nothing divided by -2/3. We end up with -1. How many sign changes? One, two. Do I hear a 3? Sold. We had 3 roots. You better not say 4, right? So don't go bidding up to 4. You could have had 3, but in fact, how many do we have? How many sign changes do we have? 1, don't we? We have 2 negatives, 2 positives, but they're in the order such that we only have 1 sign change. What's that tell us? So we have 1 root in the right half plane. The S2 row was all 0. What does that imply? How many roots are symmetric with respect to the origin? The S2 row being 0 says that the symmetry is due to the row just above it. So the S cubed row is what's giving us symmetric or symmetry with respect to the origin. And how many roots are in an S cubed polynomial? 3. So the S2 row being all 0 actually implies that we have 3 roots that are symmetric with respect to the origin. And do you see what kind of possibilities you might have? In general, how could you have symmetry with 3 roots in the S-plane? going to always have one at the origin, aren't you? That odd guy is going to be sitting there. And then you could have this, or you could have this. And there's two cases of symmetry. You could have an A and a minus A, and a JB and a minus JB. Which case did we have? We have the one on the right, don't we? We had one root in the right half plane. If we had no sign changes, which case would we have had? We would have had the leftmost case because we had no roots in the right half plane. We still don't like that system, do we? But it's better than the one on the right. But it's marginal. We'll figure out where we begin on Wednesday, but the exam, your homework is due Wednesday, and your exam is on Friday.